In classical mechanics, we come across terms like generalized coordinates, generalized velocities, and constraints. Today we are going to talk about the constraints. Constraints can be classified into holonomic constraint, non-holonomic constraint, Exclusiveness constraint, randomness constraint, conservative, and dissipative constraints. So we are going to talk about them one by one, but first of all, let's take example of constant motion. Let's take a simple example of the pendulum. So here is the pendulum. This is the point of suspension S here, and this is the point mass here. And this is the string. We take it as inextensible, so the length is always L. And here, of course, here is it moves. It's also L here. The new point P dash. And what's the condition of the motion? The condition is that the distance of the point mass. Say this is the point mass, and the suspension point is all the same, and that is L because the string is inextensible. And so we can write it. Say the R is the distance between the point and the suspension point. So R is always L, or R minus L equals 0. Let's say this is equation 1. Now, the holonomic constraint can also be defined as the constraint that can be expressed in the form, the equation of constraint can be expressed in the form of if R1, R2, dot, dot, t equals 0. This is the form of holonomic constraint. We call it equation 2. And as we know, the equation 1 is of the form of equation 2, so this is example of holonomic constraint. One more example of holonomic constraint, let's say. This is here the Cartesian system. Again, this is a circle. This is the origin. Let's take a point here, constraint to move by the circumference of the circle. Say this point, of course, this is the origin also. Let's say A is the radius of the circle. And at any point of time, say the R vector is the position vector of the particle B. And so what's the condition here is that R vector, the modulus of R vector, that is the distance between the origin and the point on this circumference of the circle, is always equal to the radius. And this implies that R minus A equals 0. Of course, the equation 3 is also of the form equation 2, so this is also an example of holonomic constraint. So the constants are of type holonomic and non-holonomic. Again, of course, this is like, what is a non-holonomic constant? So suppose this is not a circle but a sphere. So what happens in a gravitational field where R is the position vector of the particle relative to the center of the sphere? The particle will first slide down the surface and fall off. And so what will the equation of the motion here? The equation of motion would be like if R vector is always greater than or equal to a, where is the circle, the radius of the sphere here. So when the motion is happening on the surface, this is greater than A. This is equal to when the particle fall off, then this is actually greater than A. This implies that R minus A greater than or equal to 0. Of course, equation 4 is not of the form equation 2, which is the equation of the holonomic constant. So this is not a holonomic constant. This is actually an example of non-holonomic constant. In a similar way, the constraints can be classified as randomness and exclusiveness. So randomness constraints are those which contain time as explicit variable, and exclusiveness constraints are those which does not contain the time as explicit variable. For example, here the constant motion does not contain any time term here explicitly, so these are kind of randomness constraints, and those which contain time as explicit variable is called exclusiveness constraint. Again, one more classification is given by like conservative and non-conservative, or dissipative, we can say here. So again, we know that constraint has some force. Like here in here, the constant force is the tension force of the string by which the point mass is suspended. And of course, the tension force and the velocity particle always perpendicular to each other. So there's no work done by the tension force, or we can say that there's no work done by the constant force here in the case. So there is force. There is force actually, but there's no work done by the constant force, and so the total mechanical energy of the system is always conserved. And this type of constraint is called a conservative constraint. And in the case where the constant force actually does work are called the dissipative, where the total mechanical energy is not conserved. For example, let's suppose there is a floor having some friction, and there's a block, and we push the block here in this direction, and the block moves here. But the friction now, the floor actually tries to oppose the motion of the block, and when it tries to oppose the motion of the block, of course the mechanical resistance of the system is gonna decrease, and it will convert in the form of heat or sound like that, and so this is called a dissipative kind of constraint. So friction is a dissipative kind of constraint. Well, in case of this, if this is a circle, so the normal force acting on the point mass here is also conservative, because this does not do any work. So the simple thing here is that the constraint which does work, while most are not conservative, they are dissipative, and which does not work is called the conservative. Thank you.